All right, we're on to chapter 11, and chapter 11 is going to function for us as largely, um, I don't know, a continuation of chapter 10 in a very natural kind of way. We're going to prove a theorem in this video, and I guess by prove a theorem, I mean best like gesture vaguely at a theorem because the proof will be very, very, very straightforward that explains what are the possible isomorphism types of cyclic groups. So in order to do this, let's start with, as we did last time, just a little bit of a reminder slash definition. So the order of a group itself, a whole group, and it is equal to the number of elements of G if G is finite, or infinity if G is infinite. And what's nice about this concept is that if G is cyclic, then we can write G as generated by some specific G. We know from last time that that's either Z mod NZ or Z itself. But in either case, the order of G is the same thing as the order of little g, because every element of big G is a power of little g. And we saw last time that all those powers are distinct. And so there is an element of G for every power of little g, and we're happy. So with this in mind, what's our little theorem say? There are essentially, I don't want to say that. That's misleading. How about we say it this way? If G is a cyclic group, then G is isomorphic to Z mod NZ when the order of G is n, some finite number, or Z itself when the order of G is infinity. And so how does such a proof go? Well, in the last video, we discussed the order of specific elements, and now we're going to be basically just leveraging that order discussion as follows. I need to construct an isomorphism G from G to one of these things. I could probably split this up into two different cases, but the two cases are basically the same. So we're going to wave our hands just a little bit, and you guys are going to see how the pieces fit together. We define our isomorphism by sending the generator to 1. And in Z mod NZ's case, right, that'll of it, this is to be interpreted mod n. And in Z's case, it's not, right? It's just normal, good old fashioned 1. And why is this an isomorphism? Well, we check the isomorphism equation and we check that it's bijective. So the isomorphism equation essentially follows from algebra rules, right? If G goes to 1, then G times G, or G squared, right? Phi of G squared would be phi of G times G, or phi of G, or 1 plus 1, right? Because the operation in the target is normal addition, and that's just 2, right? So G squared goes to 2, and so on. And so the isomorphism equation is forced to hold by exponent rules, right? Just in general, we know G to the A, G to the B equals G to the A plus B. And since this turns multiplication into addition of exponents, we're happy, right? Because this target thing will always just be whatever the exponent is. And it's bijective for essentially samey reasons, right? It's injective because, well, in order for it to fail to be injective, we would have to have two elements that would be mapped to the same exponent in spite of being different. And we know that doesn't happen because of our discussion of the order from last time. And it's surjective because we are choosing this n to be exactly the same as the n of the order, right? So we know that we'll always have, enough elements to hit every representative of z mod nz, or in the case of z, you just keep going forever anyway. So of course, every element is hit. You want to hit, -9 or something, just take g to the -9 power. So in essence, this is the proof. On the other hand, that is extremely brief. I'm noticing we have not covered anywhere near the usual amount of time. So let's squeeze in one more theorem rather than make it its own separate video. If G is a cyclic group and H is a subgroup of G, then H is also cyclic. And before getting to the proof, I want to do two things. First is I want to wax poetic a bit about why you might care about this. In general, one of the themes of algebra that we're hopefully going to get to explore in these videos is that when you have mathematical objects that are unfamiliar to you, one of the ways that you can really familiarize yourself with it and get a sense of how to work with that object is by looking at the sub-objects. Now, I know that's very vague because I'm talking about objects in some kind of abstract sense, but what I mean is that, for groups, for example, if I give you some random group and you want to understand how to work with it, you can start by taking the elements and looking at all their powers, right? Those would be all of the cyclic subgroups generated by any given element. Then you might want to know, okay, what is the group generated by two of these elements? Do these two elements give me everything, like in the dihedral group, where everything is rotations and reflections? Do I need more elements to get everything? In general, working out the nature of the subgroups gives you a very tangible way of understanding how the elements of the group fit together in the bigger context of the whole group. And so this is a reasonable question then. It just so happens that for cyclic groups, the answer is a little bit boring. And that's kind of a good thing, right? Because we would like cyclic groups to be pretty easy in light of what we're saying here, right? That there's not that many ways that you can make different cyclic groups in the first place. The other thing that I want to do before I prove this theorem for you is I'd like to show you just a simple example so you can get an idea of what's going on with the proof. So, for example, if I look at z mod 6z, this has two cyclic subgroups. We have the group consisting of the elements 0 and 3, which is isomorphic to a z mod 2z. Notice that it's isomorphic to z mod 2z, but the elements are not 0 and 1 mod 2, right? They're 0 and 3 mod 6, but 3 plus 3 is 6, which is 0 mod 6. Very important. And the other possibility is 0, 2, and 4, which is isomorphic to a z mod 3z, even though, again, the elements are not 0, 1, and 2. It's isomorphic to z mod 3z. And that's it, other than the stupid groups. I mean, there are always two stupid subgroups. There's the group consisting of just 0, right? A trivial group. And then there's also the whole group, right? These are both subgroups of z mod 6z, but they're not interesting subgroups. So in other words, what we're seeing here is that the subgroups of this cyclic group are determined by the factors of 6, right? We have 2 and we have 3, the factors of 6, and the smallest non-zero element that you see in the group is what you get when you divide 6 by 2, you get 3, or 6 divided by 3 is 2. All right, with that in mind, let's look at a proof. So we have G a cyclic group, and we have H a subgroup of G. Since everything in G is all powers of G, the same is true here. all powers of little g. Therefore, let S be the smallest such power of g in H. Okay, so now what I'm going to do is we have to prove every element of H is a power of g to the s, right? In this example, every element is a multiple of whatever that smallest thing is. So suppose g to the t is in H for some t. Well, we know from last time how to do the division algorithm. So since s is the smallest, by division, we have t equals qs plus r with quotient and remainder. And therefore, g to the t equals g to the qs plus r, or g to the qs, g to the r. And I want to prove that the element in here is a multiple of s. So it seems to me that the simplest way of doing that is to start by solving this for g to the r. So let me, sorry about that. Let me multiply both sides of this equation by g to the minus qs. And of course, on the other side, they just cancel. And then we can do a little bit of rearranging if we want to. For example, I could write this as t minus qs. And I'm trying to think, is that the best way to see kind of what's going on here? Maybe I could do a little better by writing this as g to the minus s, or maybe even just the plus s, to the minus q power g to the t. Yeah, this seems reasonable to me. And so now what do we see here? We know that g to the s was in H because it was the smallest element in some H. And we assumed that g to the t was in H. So since these two elements are in H, in particular, this guy is in H because it's a subgroup, right? If I just raise this to some power or invert it, that's also going to be in H. And so together, both of these things tell us that g to the r is in H, right? Because this is equal to that. So, therefore, if a to the r is in H, or sorry, a to the r, g to the r is in H, we must have, since s is the smallest, we must have that r is at least s. But this is already a little bit of an issue for us, though, right? Because s is the smallest. So what does that mean? We haven't reached a contradiction. The only issue is that when we wrote down this assumption here, when we did the division, the requirement on the remainder is that r be less than s. Well, if r was 0, there wouldn't be any problem. So r is 0, there is no remainder, and therefore our t power is actually just qs. Is a power of g to the s, which is what we wanted. All right, I think we'll wrap that up here. I think this is a good place to stop. We're going to pick up now with a whole smattering of problems, just like our usual workflow. See you in a sec, friends.